In this video, we're going to look at a new topic that we're going to be working on for the rest of the semester. But before we do that, there's a little review here, just some basic derivatives that we should be able to find. So we've got here 11 functions, y given as a function of x, and we want to try to remember how to find the derivatives of each of those. We want to find dy dx for each of those. So a good idea would be to pause the video, try to write down all those derivatives, and then restart the video and check to make sure that you have all those derivatives correct. All right, so go ahead and pause. All right, so if you've restarted the video, we're going to go through and write down all these derivatives. Hopefully these are what you came up with when you did them yourself. All right, so for the first one, y equals 1/7 x to the 7. That's a really easy one. We just bring down the exponent, so 7 times 1/7 will just be 1, and then x to the 6th. All right, the next one, that's just a basic one we're supposed to know. Derivative of ln of x is 1 over x. Derivative of the sine function is cosine. Derivative of the cosine function is negative sine. The derivative of the tangent function is secant squared of x. Derivative of secant, hopefully you remember that one, secant x tangent x. All right, these inverse trig ones, a lot of people have trouble with these, so hopefully you've got those down now though. Derivative of tangent inverse of x is 1 over 1 plus x squared. Derivative of sine inverse of x is 1 over the square root of 1 minus x squared. Derivative of secant inverse of x, dy dx, equals 1 over the absolute value of x times the square root of x squared minus 1. All right, this next one, we've got a sum of functions here, but when we differentiate, we can just go through term by term, and those constants out front will just come along. So the derivative of 4x cubed, I'm going to just take that 4 times the 3, and I'll have 12, and subtract 1 from the exponent. And then on that next term, the 2 will just come along, then times the derivative of the sine function. And then on the last term here, the 3 will just come along, and then the derivative of e to the x is just e to the x. All right, and then this last one, there's a little chain rule here. So I have dy dx equals the derivative of the ln function is 1 over whatever's inside the ln function, and then I need to take that times the derivative of what's inside. So the derivative of negative x with respect to x is negative 1. And if I simplify that, the negatives undo or cancel each other out, and I just end up with 1 over x. All right, so hopefully you had all those okay. Those are just some derivative rules. What we're going to be working on now is actually undoing those derivative rules. So we're going to start with a function that is a derivative. So we'll be starting with functions like this, and then we're going to go back the other way to recover the original function. So when we do that, and we're going back the other way, we'd call that finding an antiderivative. So that's what we're going to work on now, is finding antiderivatives. And the basic idea with that is that you're just undoing differentiation. All right, so we're going to look at a couple more examples and then talk about some of the symbols that we use to find antiderivatives and how we talk about those. All right, so here are a couple more problems that we're going to talk a little bit about. So the first one asks us to find a function whose derivative is 2x. So we have a derivative and we want to recover the original function. So the idea here is that our dy dx is 2x, and we want to know what is the y function. So that one's pretty easy. You can probably pretty easily figure out that y equals x squared works. Right, the derivative of x squared is 2x. That one's pretty straightforward. All right, the next one says find a different function whose derivative is 2x. So same derivative, but I want to think about what other functions maybe I could differentiate and I would still get 2x. All right, so I have to have y equals x squared in there in order to get the 2x. But then the other thing that I might have is just some other constant at the end, maybe a plus 1. Or maybe y equals x squared minus 7. but some constant term at the end. And remember, when you differentiate that constant term, the derivative of that constant term would be 0. So there's a lot of different ones I could write down here. Essentially, pick your favorite constant at the end, and that would be an answer for both of these first two questions. All right, this last one here is what we're really going to focus on for most of what we're going to be working on the rest of the semester, finding all the functions whose derivative is 2x. And we have some notation to indicate that. So mathematicians don't tend to like to write things out in words too often. So we have some notation that would indicate find all the functions whose derivative is 2x. Okay, so first of all, we have the function 2x that we want to undo differentiation of. So that is a function we want to find the antiderivative of. And then the other thing that I want is a couple of symbols, and actually these are sort of like parentheses in that these symbols always come in pairs. So we have this one symbol in the front which looks like an elongated S. Symbol in the front that looks like an elongated S, and then at the end I'll have a dx. That's a differential. We worked on differentials in the previous week's material. That differential with respect to x. And so these two symbols that I wrote here in purple in some ways are like parentheses. They're enclosing that function 2x that I want to find the antiderivative of. This long S looking thing at the beginning is called an integral symbol, and the dx at the end here is a differential like we talked about last week. And it is telling us that we want to undo that differentiation that would have been done with respect to x. So it's telling us that the derivative that would have been found was a derivative with respect to x. And that may not seem important right now, but if you keep going in calculus, you'll end up eventually doing multivariable calculus, where you'll have a lot of different variables, and it'll be important to know how the derivative was taken with respect to what variable. Okay, so I have an integral symbol, a function that I want the antiderivative of. That function is sometimes called the integrand. The 2x would be the integrand in this case, and then the differential at the end that's saying the derivative was taken with respect to x. So I know it wasn't some other variable in the problem. Okay, so this is the notation that we would use that means find all the functions whose derivative with respect to x is 2x. That whole thing, the long S symbol, integral sign, the integrand, the function 2x, and the differential dx all together are called an indefinite integral. We will later do definite integrals, which are related but not the same thing. All right, so that whole thing is called an indefinite integral, but it's basically asking us to undo a derivative. We also maybe call this kind of problem an antiderivative problem. All right, so that's the symbols we use to do it. Then the other question might be, so what is the answer to that? So I want all the possible functions whose derivative is 2x. So I would write, if I wanted to write this problem out, all the functions whose derivative with respect to x is 2x. And then I'm going to write equals, and then I'm going to write down all the possible functions whose derivatives were 2x. So they're going to be x squared, and like we talked about up above, plus any constant. And so we have this plus c here at the end. What that plus c represents is any constant, or maybe all the constants. So I want all the functions whose antiderivative is 2x. So x squared plus every possible constant you can think of would be all the functions whose derivative is 2x. When we write this answer, so that's the answer to our problem here. When we write this answer, we also call that answer a general antiderivative. All right, the plus c is what makes it a general antiderivative instead of a specific or particular antiderivatives. All right, so we're going to spend quite a bit of time on antiderivatives this week and the next few weeks, so we'll learn a lot more about them, but we're going to look at one more little example in this video, and then we'll look at some other stuff in the next video. All right, so here is a similar problem to the ones that were up above, but a little bit different. So we want to find the function f of x with f prime of x equals 2x. So there's our derivative with respect to x. And then this other information that's given is an input-output value on the function f of x. So we can think about this in a couple different ways. We can think about this as a point 3, 1 that is on the graph of f of x. We can also think about that when I input 3, the output is 1 for f of x, and this is asking us for a specific function antiderivative. All right, so one way that I might write that up is to say, first of all, I'm going to find the general antiderivative of 2x. So that would be a function, all the functions whose derivative is 2x. That would be x squared plus c, right? So our function is going to be of the form f of x equals x squared plus c. But then I'm given this other information here that helps us identify which of these functions it actually is. If you think about what this function represents, f of x equals x squared plus c, that's a whole bunch of different parabolas that are shifted up and down from each other. The plus c just shifts that graph up and down. And I want the particular parabola that goes through the point 3, 1. Right? And the graph not to scale there. So I want the particular parabola that goes through the point 3, 1. All right, so I can think about that as a point. I can think about that as an input-output pair. But the output, or the f of x, is going to be 1 when the input, x, is 3. So I just put in an output of 1, input of 3, and then I can figure out what my c is. So when I just solve this little equation, I have 1 equals 9 plus c. Or when I solve for c, I get c equals negative 8. All right, so the actual function that we're after here that goes through that point would be y equals, or I'm just going to write it as f of x equals x squared minus 8. That is the particular antiderivative that goes through the specific point we were given, instead of wanting all the antiderivatives that go through lots of different points. Okay, we'll look at some more examples and talk about some more theorems in the next video.